Here is the message designed into sections in space or like a texture like elastic like a trampoline net transform this trampoline net into a pretzel and permit yourself to go in reverse in time. We had the option to go from Earth to the moon across 250,000 miles of space, land on the moon, and then return to Earth due to Newton's understanding of gravity. Albert Einstein, the extraordinary physicist, once said that gravity is an illusion. Einstein had dedicated his career to uncovering the truth of gravity, disproving Newton's widely held beliefs, and answering baffling time travel questions. Why is there only one way in which time travel exists when you travel at the speed of light? Why does time slow down? The latest theories and discoveries made by modern physicists attempt to provide a radical hypothesis of time to explain the unexplainable. Now, let's learn more. The gravity theory of Newton, disproving Newton's gravitational hypothesis. People didn't begin to seriously question their surroundings until the 1500s. The ancient Greeks believed that gods and divinities could explain and sustain everything, but by the 1500s, scientists like Galileo and Brahe had established that Earth was a planet, not the center of everything. The planets in our solar system orbited the sun. Kepler went one step further, describing how planets and their moons moved along their axes in an elliptical, not a perfectly circular orbit. Newton followed in the 17th century. The world has heard of the English physicist who accidentally discovered gravity after an apple fell on his head. It is now accepted, however, that Newton didn't just stumble upon the theory of gravity. For years he had been observing still objects shift from their steady positions due to some unexplained force. Yes, this also involves seeing apples fall from trees. After hours of study, Newton finally proposed that this magnetic force was gravity. He was also able to advance Kepler's elliptical orbit hypothesis. Due to this discovery, the moon, which is the closest celestial body to Earth, is able to orbit the planet because of a straight line tangent that crosses Earth's center, holding the moon in place beneath the planet's gravitational pull. Enter Einstein and his theory of relativity. Before Brian Cox tested Newton's theories, there was Albert Einstein. The famous physicist didn't explicitly disprove gravity, but declared that Newton's ideas were one-dimensional. Einstein's general theory of relativity proposed that effort and space bend, leading to gravity. He went further, defining the fabric of space-time as a sheet with D where weight exceeds an edge. Einstein also asserted that a clock placed within Earth's gravitational field would run slower than one outside its orbit. Gravity, he demonstrated, exists between any two objects, whether planets in orbit or marbles on a tabletop, and is governed by the inverse square law. According to this law, gravity is inversely proportional to the square of the distance between two objects and directly related to their masses. Einstein's ideas extended to time. He claimed the laws of physics applied to everyone not traveling faster than light. Space and time are the same things. The space-time continuum and gravity results from a warp in this continuum. Brian Cox's perspective, though no one is regarded as one of the greatest physicists, contemporary physicists like Brian Cox note that Newton didn't fully define gravity. Cox argues that Newton merely attempted to explain a fundamental concept already widely understood and accepted. One reason for this limited exploration could be the dominance of religion over science. In Newton's era, a religious man himself, Newton stopped short of developing the theory beyond attributing gravity to a sentient substance controlling planets and the solar system, challenging the rules of physics to defy gravity and physics. One must challenge existing norms. Applications of time dilation. Time dilation, defined by the theory of special relativity, demonstrates that a Moving clock in an inertial frame ticks slower than a stationary clock. This principle could propel time travel at least in theory. For instance, travelers in a fast vehicle could reach their destination a few moments sooner than those stationary experiments conducted on the International Space Station showed astronauts experienced a 20-millisecond delay in time due to their high speed. Einstein used the concept of a light clock to describe relativity, where a light beam travels in a straight line for an observer at rest. A light beam seems to have a greater distance to cover. Einstein argued the speed of light is constant regardless of motion. Thus, time isn't constant. It can stretch and contract based on the circumstances. Everyday applications. Einstein's theories have led to practical applications such as GPS navigation. GPS systems exchange signals between devices and satellites orbiting Earth. These satellites in space experience time dilation due to weaker gravitational forces. Relativity suggests that time is not an absolute construct but a relative experience influenced by speed and gravity. This leads to mind-bending possibilities such as time travel and variations in the perception of events, depending on the observer's frame of reference. The twin paradox, one of the most famous thought experiments derived from Einstein's theory, is the twin paradox. Imagine two twins. One remains on Earth while the other travels at near light speed into space. Upon returning to Earth, the traveling twin would have aged far less than the twin who stayed behind. This paradox demonstrates how time dilation works at extreme speeds. While fascinating, this concept remains largely theoretical, as humans cannot yet travel at the speeds required to observe this phenomenon on a significant scale. Length contraction. Another implication of relativity is length contraction, which states that objects moving at high speeds appear shorter along the direction of motion to a stationary observer. For example, a race car speeding by at an incredible velocity might appear slightly smaller than it actually is. If we could observe an object moving at the speed of light, the degree of contraction would be even more dramatic. This effect, though subtle in everyday life, is critical in understanding high-speed phenomena in physics. Practical uses of relativity. Apart from GPS navigation, other applications of Einstein's theories include one particle accelerators. High-speed particle accelerators rely on relativistic physics to understand how particles behave at nearly the speed of light. These experiments have led to groundbreaking discoveries in particle physics, including the Higgs boson. Astrophysics. Einstein's general relativity is foundational in modern astrophysics. It explains the behavior of black holes, gravitational waves, and the expansion of the universe. The detection of gravitational waves by LIGO in 2015 was a direct confirmation of predictions made by Einstein a century earlier. Nuclear energy. The famous equation, energy equals mass times the speed of light squared, explains the immense energy released in nuclear reactions. This principle underpins both nuclear power generation and atomic weaponry. For time-keeping atomic clocks, the most precise time-keeping devices, account for relativistic effects caused by gravity and motion. These clocks are critical for global communication networks, scientific research, and navigation, pushing the boundaries of time and space. Physicists continue to explore the mysteries of time, gravity, and the universe. Theories such as string theory, quantum gravity, and the multiverse attempt to unify general relativity with quantum mechanics. While these ideas remain speculative, they challenge our understanding of reality and open doors to revolutionary advancements. Could we travel through time? Time travel remains one of humanity's greatest fascinations. while special and general relativity suggest it might be theoretically possible under specific conditions, e.g., wormholes or near light speed travel. Practical implementation faces IM. Challenges 1. Energy requirements. Traveling close to the speed of light or creating a wormhole would require an enormous amount of energy far beyond current technological capabilities. 2. Causality paradoxes. Time travel introduces paradoxes such as the famous grandfather paradox, where a traveler could potentially alter the past and affect their own existence. Resolving these contradictions would require new laws of physics. 3. Stability of wormholes. Wormholes, if they exist, would be unstable and prone to collapse. To stabilize a wormhole for time travel, exotic matter with negative energy density would be required, a substance that is purely hypothetical at this point. Final thoughts. Einstein's revolutionary ideas reshaped our understanding of the universe, challenging us to think beyond our intuitive experiences of time and space. While some concepts like time travel remain in the realm of theory, their exploration pushes the boundaries of science and human imagination. Who knows? Perhaps one day advancements in technology and physics will turn these mind-bending ideas into reality forever, altering the way we perceive and interact with the cosmos. The planet is enormously less. Envision briefly that extraordinary relativity wasn't explained. Most importantly, there would have been no such thing as an exceptionally exact navigation system with real applications. Second, even if they existed, they wouldn't be useful, since they would be inaccurate. It's hard to imagine a world without navigation systems, and the main reason we have them and use them effectively is that the organizations that launch satellites into space account for special relativity. This allows them to consistently measure the effects of time dilation and produce reliable results. The theory of general relativity. Nearly a decade later, in 1915, Albert Einstein published his theory of general relativity. This theory proposes that gravity is a result of mass warping the space-time fabric, disproving the idea that gravity is an inherent force existing in all matter. To grasp general relativity, you would need to picture the universe in 4 dimensions, 3 for space and 1 for time. Now imagine that each point in this 4-dimensional universe could contain planets, stars, or even ordinary people. Naturally, they would be able to bend or stretch the space-time dimensions simply by virtue of their mass. Gravity, or at least what we think of as gravity, originates from this warping. According to Newton, gravity is an innate force that the Earth has and is responsible for directing everything toward its center. According to Einstein, space-time works as a fabric, and that's why objects are drawn toward the center of the Earth, not by a force. Here's a better way to visualize this picture. A long trampoline. Now place a bowling ball on the trampoline at a random location. It's clear that the bowling ball's mass is sufficient to cause a dimple in the trampoline. Step onto the trampoline and throw a marble onto it. What happens? The marble naturally moves toward the dimple created by the bowling ball. You'll notice that heavier objects like tennis balls don't fall toward the dimple as easily as the marble does. Similarly, if you replace the marble with something comparable in mass to the bowling ball, such as another bowling ball, it wouldn't roll toward the first ball's dimple. Instead, it would create its own. This exaggerated explanation mirrors what happens when considering the Milky Way's behavior under space's fabric. The moon is our natural satellite, and the space created by Earth's mass draws the moon toward it, keeping it in orbit. The moon's weight is insufficient to resist Earth's pull entirely, but it's enough to exist in its own space on the space-time fabric. The main reason the moon isn't falling freely like Earth might be drawn toward the massive sun is its significant mass which prevents it from crashing into the sun. Newton. Gravitational laws failed to account for gravity's true effects and their influence on our environment. A practical use of general relativity. A practical demonstration of general relativity occurred in 1919 during a solar eclipse. Massive stars are large enough to escape the sun's curvature, but a lighter star may get trapped in its curve, causing its light to bend when measured on Earth. This bending displaced the star's light, confirming this bending effect. Einstein's general relativity emerged as a groundbreaking milestone. Building on general relativity, Einstein's theory revolutionized our understanding of gravity and its interaction with light. One key prediction of this theory was the bending of light around massive objects, an effect known as gravitational lensing. This phenomenon occurs because the mass of a large object, like a star or a black hole, warps the fabric of space-time, bending the light's path as it passes near the object. In 1919, during a solar eclipse, British astronomer Arthur Eddington conducted an experiment to observe this effect. His findings confirmed Einstein's predictions. This was a pivotal moment for general relativity, as it provided experimental evidence that light, previously thought to be immune to gravitational effects, could indeed be influenced by gravity. Gravitational lensing has since become a critical tool in modern cosmology. It allows astronomers to observe objects that would otherwise be too distant or faint to detect. By studying how light bends around massive objects, scientists can map the distribution of dark matter, a mysterious substance that doesn't emit light but whose presence is inferred from its gravitational effects. Sometimes gravitational lensing can magnify distant galaxies, offering a glimpse into the early universe. Understanding black holes, Einstein's theories also laid the groundwork for understanding black holes, regions of space where gravity is so intense that not even light can escape. The existence of black holes was predicted by general relativity, but it wasn't until the 1960s that astronomers found the first indirect evidence of their existence. Today, black holes are a major focus of research, with scientists using advanced technologies like gravitational wave detectors to observe their effects on nearby objects. In 2015, the Laser Interferometer Gravitational Wave Observatory LIGO made history by detecting the first gravitational waves, ripples in space-time caused by massive events like black hole collisions. This discovery provided further confirmation of general relativity and opened a new era of observational astronomy, challenges and future questions. While general relativity explains gravity on large scales, it doesn't account for gravity's behavior at quantum scales. This discrepancy is one of the major unsolved problems in physics. Scientists are working to develop a theory of quantum gravity that would unify general relativity with quantum mechanics, the theory describing particles' behavior at the smallest scales. One contender for such a theory is string theory, which posits that the universe's fundamental building blocks are not particles, but tiny vibrating strings of energy. String theory suggests that gravity, along with other forces of nature, can be explained as the result of these vibrating strings interacting with one another. Another significant challenge in physics is understanding the nature of dark energy, a mysterious force driving the universe's accelerated expansion. Although dark energy makes up about 70% of the universe's total energy, scientists have yet to fully understand its properties. Some theories propose that dark energy could be related to the properties of space itself, potentially linked to the cosmological constant introduced by Einstein. The study of time travel, another concept arising from Einstein's theories, remains an intriguing but largely speculative area. of research, while special relativity allows for the possibility of time dilation, where time slows for an object moving at relativistic speed. General relativity also suggests that time travel could theoretically be possible under certain conditions. Wormholes, for example, are hypothetical shortcuts through space-time that could allow for faster-than-light travel between distant points in the universe. Although wormholes remain purely theoretical, they are a fascinating area of research within general relativity and quantum mechanics. Despite advances in our understanding of the universe, many questions remain unanswered. What is the true nature of dark matter and dark energy? How do quantum mechanics and general relativity fit together? What lies beyond the